Welcome to Beyond the Qubit. I'm your host, Frank Dekker. The guest of today is Thomas Ohki. Thomas is the CTO of Emergence Quantum. And I really look forward to interview Thomas because Emergence Quantum is a special company. At the moment, they're not yet relying on external financing. They're funded on customer and partnerships. And Thomas has a lot of experience. He has a long tenure in the quantum industry and he tries to optimize for the long term. And he tries to solve bottlenecks in the quantum value chain. And the specific focus of Emergent Quantum is cryo-CMOS, but they have multiple, they research multiple problems across the value chain. Before we start the podcast, I have an important disclaimer. The podcast is under personal title and I do not represent any company out there. With that, let's get started. Welcome, Thomas. Glad to have you here. Today we have Thomas Ohki, CTO from Emergent Quantum. Thomas, can you...
Well, thank you. Yeah, thank you so much for having me. Nice to meet you, Frank, and I'm looking forward to the show today.
Can you give us an introduction of your background? And maybe as a starting point, can you walk us through your journey into quantum technologies? What sparked your interest first, and how did you arrive at your current role?
Right. So you can tell from my accent that I'm in Australia at the moment, but I'm from the US originally. My background has been really, I'm a physicist. I worked after PhD, for a long time, I worked for a company called Raytheon BBN Technologies, where I led the quantum division there for many years. And then since then, actually moved to Australia, worked for Microsoft Quantum for a little while, and then now started a new chapter, a new company called Emergence Quantum, where I'm co-founder with David Riley, who's a professor at University of Sydney. We started this company, and right now, I'm CTO, CSO of that group. After many years of being there, during COVID, I moved to Australia. I have family that's Australian, and so we tried to it was an unusual time to move, but we did during that time. I led things remotely, which also was sort of only something that could happen during COVID. But went to Microsoft after a bit of time because the pull there was that Microsoft had this really big program that was exploring very specific technology. And it seemed like an interesting opportunity because I came from a background where it wasn't a company that was going to invest a lot of money just in one particular direction for a product, right? We were looking at research. Microsoft was kind of the opposite, investing a lot of time and money into a product. So it was a different way of thinking about it, right? And also was exploring systems that had a nice hybrid of things I was interested as well, superconducting, semiconducting, control systems. David, who is here at University of Sydney, worked with MS for a while, and I knew him from 30 years ago that we essentially were working on projects in a similar direction. So we had always been tracking a little bit the same way as our interest grew in quantum computing. And it was more from the perspective of not necessarily focusing exactly on how do you make the qubits the best as you possibly could, but also how would you grow that beyond what it is, in the early days to, not a few qubits, not even tens of qubits, but thousands, hundreds of thousands. There's some really fascinating problems, and probably both of us were a little bit too early in thinking about those in the maturity of the field, but quite frankly, that shaped how we've been thinking about it and where we are today. And that is a long answer to your question of how we got to Emergence, which is we both philosophically felt this was what we were interested in, what we thought from the quantum computing side, our best, focus, or at least our interest would be focused on, the best utility of where, our skills and the group that was massed together and everything sort of seemed to point in that direction of this is the type of technology we should work on, things to help scale. That's really where Emergence is coming from, is that we're a company that wants to do a lot of the research to solve hard problems, kind of the things that I was working on before at the company, like really the bleeding edge problems, things that are a few years down the road as far as we need to implement something to correct now, but also try to do that at a scale of a a company which is really accelerating and trying to build towards products. So the fusion of those worlds, where it's engineering and development towards a useful system, but challenging problems that are along the way that need to be tackled, and having a bit of a research but product mindset and building that up, that's kind of the core of where we think Emergence is going, what its strength is, and what we want the company to be known by, and what our mission is. And that is just particularly the quantum computing side. So that's the evolution. That's sort of why we ended up where we are.
Can you maybe, I would love to better understand what are your fundamental beliefs. And typically fundamental beliefs are shaped by lessons from the past. Do you have 3 bottom-up examples that describe lessons that you transferred into beliefs and that can help Emergent Quantum going forward?
Yeah, well, you mentioned 3, right? Or there could be a few. I think one of them that I believe, and I think David, as a co-founder, we believe pretty strongly, is that research isn't just, it's not engineering in our mindset. It's not just executing. There is an element of unknown, there's an element of failure. And accepting both of those aspects as part of the process, incorporating that with an engineering mindset, that experience shapes you to have a belief that you need to understand that failing is actually acceptable in some capacity to make progress. And there's a bit of a, in some worlds, maybe pure product development, that's not necessarily something that's a mindset. And I think that's a belief that both of us share, is that you need to have some of that uncertainty and make mistakes to make progress. So that's why I think we embrace the sector of research that we are. There's an ability to have enough freedom where we can actually move in enough directions to make those mistakes that let you correct in the right way. So without that, I think it's hard to develop technology. So that's one. So one thing I learned over time was that being part of an organization that valued being at the forefront of research, that's how you got money for contracts, right? Is if you were the one that was clearly at the top of the pile, knew what was coming, the trend, and could execute. And that was the thing that was valued. That actually was the currency you paid in, right? So even if you had larger companies with twice or 10 times the budget, if you didn't stay really at the bleeding edge and really with the top people in that field, you couldn't compete. And it's not only just getting that first contract. Once you get it, or you're working on a project, or you're trying to execute an area, you started falling behind. And the point I'm trying to make is this. The only way to get to the top of any area, particularly if you're working in industry environments, is to be reading papers, going to conferences, being in the academic sector, being in places where research is at the forefront, being active in procuring other sort of competitive grants around that area, not just relying on internal company funding to do something, or a pot of money that might be VC, like wherever the funding is coming from. If you're not actually sort of sharpening your skill set while doing that, it's not good for the overall health of you or the business. And so I've seen multiple occasions of this where actually if you back away, like the company I was part of, BBN, it was only 500, 600 people, right? But that company was one of the top defense contractor companies in the US, pulling in many contracts within top 5. And one of the biggest competitors was this company, Raytheon. It's a gigantic monolith. They ended up buying that company because it was such a competitive entity, but it was only 500 people, that they could outcompete this huge defense contractor for advanced research technology, right? And so that's a good example that you're keeping, like that company was founded on a bunch of, a lot of academics, a lot of MIT people from down the street. It was in Cambridge and Boston. So there's this startup mentality to that R&D side. And that sort of premise was, staying agile, staying at, up to speed on research, being immersed in not only immersing yourself in what the work is that's pushing technology, but also being part of the community. We would also interact a lot with academic groups, have them as subcontractors on projects, work with them closely. That actually was probably the main reason why we're so competitive, right? So I take that away as a lesson also is a principle or belief is that in order to be successful, you also, it's not money that makes you successful or the ability to pull on a large chest. That obviously helps. The hunger and the desire to keep yourself at the forefront and the drive to do that. A little bit of hunger, whether it's like not having a huge amount of resource, is actually helpful, right, to that process. And you can find analogies in life all over the place where that could be true as well. But I won't make those analogies on this. I'll keep it to the science side. But yeah, that's another belief, is that you have to keep hungry, you have to keep on the edge, you have to always be learning. And being competitive with other companies and peers, not hiding things, is one way to keep that edge, right?
Okay, that's very helpful. Maybe let's talk a little bit about Emergence Quantum. How do you describe Emergence Quantum in simple terms to people who don't know Emergence Quantum?
Yeah. We at Emergence are interested in accelerating the future of computing. Really beyond where it is today, beyond what you see in AI and data centers. What's the next generation of computing technology? What is beyond that? Whether it's next generations to AI data centers or all the way up to quantum. So the world and its desire for computing is almost unlimited. And so we would like to keep as much pace with that as possible. What the company is doing is we're providing hardware solutions to not only explore, but implement and develop paths towards those next generation platforms. And so one of those areas is quantum computing, because that's one of the really interesting areas that needs a lot of development and is going to take some time. And it's such a complex problem that it's hard not to be fascinated by it. But that's just one sector. We're looking at what comes beyond like the conventional computing systems we have now. It may not be quantum. It likely isn't. I mean, that's usually you don't take a leap that large for a variety of reasons. And there's a whole bunch of solutions, whether it's more energy efficient computing platforms or where we think cryogenic compute will be in the future of data centers, how that will impact things. And this isn't even related to quantum physics. It's related just to how do we make existing systems more high performance for the amount of watts that you're using. So those areas, that's what the company is looking into, and it's really developing hardware solutions for that. We're looking at new technologies, how new designs of materials, whether it's superconductors for different applications in compute or readout of quantum systems, or it's different modes of operation of silicon technology at cryogenic temperatures. So that's the area that we work in, and we work with a variety of customers in that space, but have an eye on what products will be relevant to the industry and community that Emergence will focus on.
Okay, and I think, but can you explain me, how did you make it possible to start up a company without external capital? Because that's really powerful, and that's really a unique achievement.
Yeah, so I will say this, that there's a bit of a story behind this as well. So I don't know how I don't know how replicatable it is, but so there's a big team that was part of Microsoft formerly that we decided to start this company and stay in Sydney, Australia, and that was after we were asked to move to US and join the team in Microsoft. But I think we collectively made a decision we wanted to try something new. So there was already sort of a unity in that. So there was a group of founders that essentially said, we're going to stick together and do this. So that's kind of unique. It's plenty, like 20 plus people already to band together and do that. That's not normal. Yeah. Generally. There's also this idea that we are in Australia, and the idea of staying here was something that there was actually a lot of people in the community, up from the government level through administration at the university where we've been, to others across the community, that the amount of support for starting something here and having that process continue to grow and flourish into something like amazing was everybody's hope and desire, right? And so that support is also a little unusual.
Thomas, can you explain in basic terms how your technology works?
Yeah, so there's three sectors that we're in. Like I mentioned, quantum computing, sensing systems, and energy efficient compute. There's a horizontal across that. And that horizontal technology is right now a lot of technology that for certain systems forms different purposes. But it's based on a lot of cryogenic electronics that's used for control and readout or energy efficient compute. But it's based on silicon CMOS technology, other 3-5 materials for different types of devices there, superconducting materials for not only RF components and logic, but these kind of discrete technologies for these functions, most often sitting in some low temperature environment because that's where we've kind of optimized the technology. And the role we play is, you can imagine, a lot of technology may sit at very low temperatures, and then you have things that obviously wouldn't be at low temperature. We form sort of the
Thomas,
connective tissue between those layers.
But then coming back, you said, okay, we have three products: quantum computing, sensing, and high performance compute. Is that correct? And then you said we try to. So my question was, how does your technology work?
Yeah.
Could you summarize that? So
the technology, how does it work, right? So it's not too different than normal digital or analog electronics. So all it is electronics that enable you to either measure a quantum system or dissipate less energy, be more efficient in computing. But if it's a transistor, it's still a transistor at low temperature. If it's a superconductor, it's, it still has its superconducting effect, so it doesn't act in a different way. What we're actually doing is enabling it to perform a function, rather than saying, this isn't us saying we're creating a new material that does this brand new property or does this new bit of physics. It's actually, there's some pretty well-known things that people have done for many decades, but engineering that, understanding some of the physics ramifications for building that hardware, particularly like things like operating semiconductor technology at millikelvins or Kelvin temperatures, low temperatures, requires you to engineer it a little bit different. You have to change the devices a bit. So it's not that it's functioning differently, to your point, but it's just more optimal for the environment that it's in. So I'm not sure if that helps a little bit.
Yes, now what pops up in my head is, yes, what are the difference between normal semiconductors and semiconductors for quantum? And I think, you have superposition and you have entanglement, and because of that, those constraints, you can use different materials and you could operate in a different environment, depending on which quantum technology you use.
That's right. Yeah. So there's one interesting thing is to expand upon what you're going with here as far as a thread. There are a variety of technological platforms that could be quantum in nature. A lot of them are operating at a low temperature now. So we can think of those as the quantum layer. As you move up in a system, there's other things that do the signal delivery or signal retrieval of that system. There's always an I/O to that quantum layer. A lot of that technology...
Recently, I interviewed Delft Circuits,
right?
The CEO, and they did the cryogenic cables, the input output.
So that the I/O, the physical I/O, is one challenge. The active components that provide signals is another challenge. Where does that sit in your system? Each qubit or quantum system has its own requirements. What I'll say is this: in really broad terms, this layer that we provide between, say, a user that wants to interface a system that comes to a room temperature system, types in a set of commands, runs an algorithm that then compiles down to instructions that goes down to a processor level at the quantum level. There's a whole bunch between those two things. Like, there's a huge amount of engineering between those two functions, right? So what is kind of a subtlety is that what our technology really does is bridge the worlds of what you would call kind of classical systems or electronic noisy things that are, higher temperature, room temperature, things that wouldn't observe any quantum effects, and connecting those things to these quantum systems. And the quantum systems are very fragile, very delicate, can be destroyed by the smallest amounts of noise. connecting those worlds up is not as simple as just taking two things and putting them together. You need this interface layer that is designed in a way that it's not, again, it's not just engineering for low temperature. It's actually engineering with an idea that you're connecting this really delicate system to this other thing that's almost like, could be the temperature of the sun if you really thought about it. They're so different in scales of energy or in the noise. Bridging that gap and still making that whole system work, that's kind of the beauty of this whole challenge. That's how this field is going to end up evolving and working in the end of the day, is whoever is successful at doing that the best and in the smartest way to make big enough systems, that's how you end up winning this.
What do you mean of that? So if you say we scale up the system, do you have an analogy like scale up and scale out? And scale out is connecting the clusters.
Yep. So scale up is what I'm primarily referring to. So in a, say, single compute platform, the equivalent of a blade, you'll have maybe multiple quantum processing units equivalent to your multiple GPUs. Maybe they'll be stacked or on other types of arrangements where you start to increase the I/O density dramatically at that plane. At that point, you could either take lines and fan out and then keep fanning out to the point where you get to discrete components outside that do control of the system, or you keep it where you're doing lithographically defined connections, or keep it in a nearby or co-located near the processing units, right? And so that your fan out is not as severe. There's fabrication challenges. It really depends also on what technology you're talking about. Like, for instance, semiconductor qubits, they have a very small footprint. It's challenging as far as the fan out to other circuitry, so that a lot of the effort is to think about how to bring local control to those technologies in particular. So you'd want to have high density control units that are providing signals that are proximal to your device, to your quantum processor, not pulling it out at any level. So we're not even talking about scale out. It's more, or connecting of computing units. This is really at what people have been calling the quantum processing unit, like the equivalent of your GPU, right? So your primary processing unit. So some technologies are like that. Some, as the number of qubits
helpful.
grow.
Thank you.
Yeah, no problem. There will be a challenge as the quantum processor densities and the number grow in a single system, that fan out to the systems that are at room temperature will become more and more challenging. And there's some platforms, like I mentioned, that natively want to, as the system size grows at the processor unit, you'll have to be closer to that processor, or even in some cases co-located nearby, even
and can you also
flip-chipped.
Design it on chip?
In some technologies, yes.
What are the pros and cons of doing that?
Well, so I've seen the spectrum of quantum devices from, say, superconductors. If you talk to companies building those systems, they'll be extremely hesitant of putting any active circuitry near the processor layer, because we've spent many years shielding it from that. So it's almost a no-go to think about that, to do anything monolithic. With other systems, like for instance, semiconductor systems, they're much more robust against thermal effects, other things that would normally harm, say, superconductors. So you can almost have them monolithic. And in some cases, that's some people's roadmap. In other cases, it's not directly controlling your single bit or anything like that. But for instance, ion trap systems, for a long time, people have been developing traps to shuttle ions around a surface to have them interact. That's their computing platform. Control electronics people have been trying to engineer monolithic control for the electrodes that actually move these ions around. And so there's a vision for all of these platforms to some degree. Each one has a different need, but a lot of them do have this requirement that there's really tight integration. It could be exactly this, monolithic or backside processing of subs, and other versions of that where it's a little bit more distributed.
Okay. Thank you. Let's go back a little bit. One of the areas Emergent Quantum focus on is cryogenic control electronics and integrated cryo-CMOS. Can you explain in simple terms what cryo-CMOS is and what solutions does it bring?
Right. So personally, I have worked on cryogenic electronics that span semiconductor technology, CMOS or superconductors. The goal is this. We'll get to the goal first. You want to create some electronics that are able to control quantum systems and not decohere those systems, which means don't spoil the quantum system. Like, you have to maintain its quantumness in order for the devices to work, whether it's a computing system or a sensor. So that means you have to design circuits that are low power enough, don't produce noise.
And Thomas, what solution gets you most excited at the moment? That you say, well, this really drives my energy, and I think that can really solve a bottleneck in scaling up the amount of qubits.
Right. So there are so many challenges at the qubit level, and I think you'd be remiss without saying there's been an amazing amount of work that's gone into that level. But I do feel like the next frontier of scaling will be to see for many of the systems that could scale quickly, meaning there's a few platforms like semiconductors could scale quickly, where those also require very close proximal circuits for control and readout. I'm kind of extremely excited, but at the same time, that is one area you can't be excited without there being some sort of risk involved. But that one seems like the most, some of the most interesting. There's other platforms that are requiring a significant amount of co-integration and co-location. How that performs in the next 3 to 5 years at some level of scale, and if you can retain performance of those systems, that has me very excited, because that means you can unlock a lot with that approach. If we find there's a fairly positive response, these systems are robust against the things that we think about, and you can actually get to a level of some co-integration that allows you control circuits or readout circuits nearby, that will be a big shift in where the field is today. I can't pin down exactly the technology that specifically makes me excited for that, but that is I would say a technology leap, which I'm excited for. There could be a very diverse set of hybridized technologies within that, and it relies on so many things that we just mentioned, right? From advanced
Thomas,
packaging and onward.
Can we talk a little bit about your recent partnership with IQN to develop electronics and materials for ion-trap systems? What is the scope and timeline here?
So with IonQ, you mean, right?
Yes.
Yeah, okay. So IonQs, we have a partnership with them that we are really looking at developing hardware that would, like I mentioned before, some of the technology for shuttling ions around requires electronics to drive electrodes and do that in an efficient manner. Obviously, things related to shuttling photons around that interconnect traps as well. But those types of technologies we're in the process of setting up projects with IonQ to explore development. They have a roadmap of their own, which I'm not going to talk about. And so our expertise, we've discussed already, is looking at how to solve some of those challenges where there's integrated trap electronics, integrated control systems that help interconnect traps and things like that. And so it's all super exciting, because it's getting to the next step is a huge challenge with those platforms. And like I mentioned, it unlocks a whole host of new opportunity if that's successful. So we are starting on that journey with them. Really, it's just something that's kicked off. We strongly believe that there's a next generation tectonic shift, if you were to say, in compute technology that actually starts to go more cryo. We're pretty bullish about that. So I think there's
Thomas, why is that? Why do you think that the next tectonic shift in compute involves cryo? Because now you got me. You have my full attention.
Right. So we do think that there's only a few knobs that you can turn to improve compute systems, conventional ones. And one of the last remaining ones that we know, it's been shown that performance can be improved as far as performance per watt, efficiency, increased clock rates, can be by adjusting temperature. And that's even with conventional CMOS. Not to mention other alternative technologies that might be a little bit down the road, but in that path, like superconducting things as well. But I'm even talking about just conventional CMOS. And so we do think that there's a path forward there where that's a very intriguing direction. And the world has changed in the last 5 years. I used to sit in meetings and, I was working in energy efficient compute in parallel to quantum for a long time. And the size of data centers, the energy cost of data centers, people were saying, 50, 100 megawatt data centers, you're not going to get much bigger than that because you need nuclear power plants to run them. And it's like, no one's going to do that, right? So things have changed a little bit, right? And so that, in addition to how people are cooling devices now, like liquid to chip and other things where the infrastructure, the energy expenditure, things that were unfavorable to alternative compute platforms are starting to, that story is changing a little bit. And so we think that there's a direction where not only, in quantum computing and quantum systems, cryogenics is almost a necessity now. There's a world where cryo starts to permeate the compute platforms that you see today and start to merge with quantum systems, edge technologies that are sensors as well. So the convergence of technologies, I think, towards the direction where you're going to be able to take advantage of improved performance by cooling even further than obviously things are done today in conventional data centers is an exciting one for us. So that's a space to keep an eye on. I think like I mentioned, we're working in that sector
Thomas,
as well.
You mentioned that there's only so many knobs to turn on, and you say, okay, if you move to lower energy in CMOS, that has benefits. But what benefits does it bring if you move to lower temperatures? Do you mean lower energy consumption, or so less heating issues?
So,
or
yeah.
I really want to understand what is the benefit if you move to lower temperatures in CMOS?
Yeah, so there's some studies over the last few decades that have looked at what happens as you cool that technology. I mean, there's some things that change immediately, like leakage effects. So you're already decreasing static power consumption of certain things. You can also lower certain threshold voltages, increase clocking rates and things like that without paying a penalty. So you're able to get more performance from just those aspects. And
why is that so? If you reduce so you said, okay, if you cool things down, then you have lower leakages or lower heat dissipation. Did you say it enables, if you cool it down, then it enables you to turn up the clock speed?
You can start to overclock circuits. You also have, the leakage effects are one thing, but you can also potentially, thermally broaden threshold voltages require you to have sort of also bigger swings and voltage across devices. So you can actually tune and change the threshold voltages. So people have been looking at low threshold devices in combination with dynamic savings in energy, because it's just your CV squared. You also have this leakage effect. So those things combined with some other aspects, optimal kind of design of circuits as well, you'll see these improvements. And it's not a matter of sort of theoretically whether that's the case. It's more implementing and making sure it's a commercially viable solution. It sort of wasn't ever, because the thought of cooling down anything beyond just with water cooling, it was basically a no-go. But so 20, 30 years people have been already doing this. In some applications, people have just absorbed the effect of doing that because they needed cryogenic implementation. Like, for instance, I was in the defense community for a long time. People built sensor technology that had to operate cold. Building readout and integrated circuits needed to happen locally. It needed to have some density. So people were forced to optimize devices for that temperature, But so there was a lot of learning already happening for the last 30 years in this community. But from the compute standpoint, there really hasn't been a lot of progress. But the analysis side, I think people have really looked into it. There just hasn't been a financial motivation to do so. But the changing landscape of compute now, and the whole evolution around what does energy consumption mean in these systems, and that's evolving everybody's thinking on the topic in general. So that's another exciting space to be. But like I said, there's these horizontals across computing, quantum computing technology that apply, like some of the tech development, like you're trying to optimize energy of the compute systems that you're building for the other platform. A lot of the challenges become kind of similar analyzing thermal properties of circuits operating at temperatures like that. Not only just how an individual device functions, but how you design a system around that and how to remove heat and things like that. So those are all sort of relevant challenges that fit across all these platforms.
Great, thank you. Maybe one final question. Can you wrap it up maybe in 1 or 2 minutes and give a summary about Emergent Quantum and why investors and people who are excited about quantum technology, why they should pay attention to Emergent Quantum?
Right. So Emergence is not just another quantum computing company. It's a company that's going to solve problems on the next generation computing platforms that span quantum systems and also what's happening in the next generation of computing platforms for AI and data centers. The reason that people should keep an eye on Emergence Quantum is because the core technology that we're working on is what is going to be the key to unlock the future for what we feel is next for quantum computing systems. And the next 3 to 5 years is where you'll start to see the impact of the technology we develop make an impact on how those systems grow. So our involvement not only in quantum sectors, but the technology we build for data centers, we're hoping that becomes a focal point, and we're pretty confident it will, in the maturation of the next phase for both of those technological areas, which are some of the largest impactful areas that I think will really revolutionize computing, not only the quantum sector, but what's the next step after hyperscalers run out of runway, right? So that is the reason to keep an eye on Emergence Quantum, and we're excited about the future.